Hi everybody, welcome to Test 3 review for Calculus 1. As always, on the top you see the list of the topics and the questions that we're doing, and the formula will be on that side. Right, now just go to the first problem about optimization. What we have here is we have the length and the girth around. The total is not more than 120. So here we want the one with the largest possible volume, and this also has a square end. So this is the square end. So if we have this x, this also x, and this also x. So x all around, and let the length be y. Right. So the first thing we have is 4x plus y is equal to 120. It is not does not exceed 120, but we want the maximum volume, so we're going to make that as big as possible, so make it equal to 120. So from here we can have y equal to 120 minus 4x. Now we have that. Next, we want the one with the largest possible volume, and the volume, this is the rectangular box, length times width times height. So pretty much x times y times x, or x squared y, and this volume is to be maximized. Right. This function has two variables, so we have to rewrite that. So it only has one variable, so we have y equal to 120 minus x. Just substitute into that, and so we have the volume is v equal to x squared and 120 minus 4x, and one function, one variable, so it's good, and the volume to be maximized. Right, it's that. So we have the function to find the maximum, which is good. Also, the one thing we need is just have the boundary for x. So we need x to be greater than or equal to 0, because a measurement cannot be negative. So we have that. And then another restriction is that we want the y to be positive as well, because that also a measurement. So we have y equal to 120 minus 4x. So we have 120 minus 4x must be positive or 0, greater than or equal to 0. And we solve for x. So we have for x less than or equal to 120. So x less than or equal to 30. So we have x less than or equal to 30. And pretty much this is the problem that we're going to do. Right, I'll just rewrite that problem. So maximize the function on the interval 0 to 30. Right, let me change this a little bit. Now to do this, we take derivative, find the critical point between this, and then we test all the points. So critical values. Critical values in between this. Critical values on 0 to 30. So we take derivative equal to 0 does not exist. Before taking derivative, I will multiply this out. 120x squared minus 4x cubed. So derivative would be easier to do. So 240x minus 12x squared, right? Derivative equal to 0. Derivative does not exist. We do not have anything here because this is a polynomial. It is defined everywhere. Equal to 0. 240x minus 12x squared equal to 0. Factor out the 12x. We have 20 minus x equal to 0. So x equal to 0, x equal to 20. And both of them between 0 and 30, which is good. And next we just evaluate on the table. Evaluate. This is the maximum minimum we evaluate on the using the original function. And this is original function. One 120 x squared minus 4x cubed. Those are the values. Right. Let me put the calculator. The calculator. Right. So I'll go to stat, edit. The list one I will have these values 0, 20. I think we did this on the second review. And then on this function, we need to highlight the L2, and with L2 highlighted, we enter the function. Instead of x, we use L1, so second 1 square minus 4 L1 cube, and we have that. And obviously this is going to be a max. The max is here. Try to change the color a little bit. Keep the contrast down. never mind. So that gives us a max. So we say the max form. The question asks for the maximum, asks for the dimension. So we have x equal to 20. So now we go back to put the calculator on the side for a minute. We have x equal to 20. So we have 20 all around here, and y equal to 120 minus 4x. Equal to 120 minus 4, 20, 80, 40. So x is 20 and y is 40. So the one with the maximum volume 20, 20, and 40. So the dimension uh, 20 by 20 by 40, and of course the unit is inches and the volume is square inches. So that is the first one. Right. Next we'll go to linear approximation. I think that's better. Now we'll go to 3 and 4. Linear approximation. So the formula, let me go to that first. So as the formula will be on that side, let me write down first. So linear approximation, to approximate a function, we use the values at a plus derivative at a x minus a. So for this problem we try to estimate that the only number we have is 145. So what we do is let x equal to 145. If x equal to 145, then the problem becomes square root of x. So we have square root of x equal to a function that we try to do. And after that, we choose the values that is very close to 145, that has a very nice square root. So that will be 145. So next, we're going to choose so we choose a to be a very number that is very close to 145, but the square root is nice and even, and square root of 144 is 12, so that's why we choose a to be 144. Right, next, since the function is square root of x, or x to the 1/2, we evaluate at 144 x equal to 144. We have f of 144 equal to 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 × 144 square root of 144 is equal to 12. So we have the values of the function at that point, and then we take derivative. And we evaluate at x equal to 144. So find the values of the function and the derivative at that point. So we have 1/2 144 to negative 1/2. So we do that. Add the calculator again. Right. We can use 0.5, but 1/2 times 144 to the power of negative 1/2. And we can change this to a fraction, 1/24. And then finally we put in to the function. So the values is 12 plus the derivative 1/24. X is 145 minus 144. So pretty much we have 12 plus 1/24. I shouldn't put the calculator there. So 12 plus 1 divided by 24, and we have that. In the spirit of approximation, we keep this in decimal and 4 decimal places. 0.41, one more, so okay, 7. That will do. So that is 3. So pretty much we let x equal to numbers, the only number in the problem, and then we choose A. We do the same thing on number 4. Just turn it off for now. Right, 4. Right, so the only number we have is negative 0.01. So we'll let x be that. Blue. So let x be negative 0.01, and so the function becomes sine of x is the function, and then we choose a number that is close to this, and the values is easy to evaluate. We choose 0 because sine of 0 is 0. Now a is equal to 0. Now we evaluate in the function. The function is equal to sine x. So when x equal to 0, f of 0 equal to sine of 0, which is 0, and derivative of sine x is cosine x. we will evaluate at 0 derivative of cosine of 0 is equal to 1. And so linear approximation just put everything we have. The values of the function is 0, the derivative is 1, x is negative 0.001 minus 0. So now we will need the calculator for this one. So we have that. And let's just quickly sine of negative 0.01. The actual values is not far off, so we at least get the first two decimal placed correctly. Right. So that is linear approximation with that formula. Let x be a number and choose a nice number close to it. Right. So we go to differentials. Differential will be just that. So pretty much we'll take derivative, and let's use the chain rule on this one. So put this in the box, and we have sine of the box, and the box is 3x squared. So we have derivative. Sine of u is cosine u. Derivative of 3x squared is 6x. So we just have cosine of u. U is 3x squared, so I would move the 6x in front of cosine of u, and cosine of u is just 3x squared. Right, so that is the derivative. Now if we write the different notation for derivative, instead of f prime of x, we write dy over dx instead of f prime of x. Then we move the dx over, and that gives us the differentials of dy in terms of dx. So pretty much just that. That is the differentials. Next, we do approximation the changing y, the delta y. Again, the formula is on that side. We should be talking about this one. Right. So first of all, we look at the problem. We see that this is the volume of a sphere. If the rays increase from that to that, so when it is increasing, this will be the x value. So we write a values is equal to 5.2, and it goes to x. equal to 5.3, and so the delta x is the final minus the initial. So increase by 0.1 centimeter. So that is the delta x. Right. Next we start with the volume. Is 4 over 3 pi r cubed. Right. So we take derivative. Will be 4 over 3 pi r squared 4 pi r squared. I think we did this one in class. Look familiar, but anyway, it doesn't matter. Now, the change in y approximately equal to the derivative times the change in x. This problem, let's change that to the change in volume approximately equal to the derivative and the change in r. So we don't have x, so let's, instead of delta x, let that be delta r. Right. Now we have 4 over 4 pi r squared. Instead of r, it's going to be at a, which is 5.2 square times delta r 0.1. Right. Just do the math and we should have it. Whatever that is. So the change in y approximately equal to the derivative at the initial point times the change in x. A is the initial point, x, or in this case r, the final point. Right. So we have that. Right. Next, the mean value theorem. So the mean value theorem is this. So on one side, the left side, we have the slope of the secant line. And on the right side, we have the slope of the tangent line. Right. Now first, we find the slope of the secant line. So that we go from 1 to 2. So from here, A is 1, B is 2. And so we do that. So put the calculator quickly here. Right. So I just store the values of 0 and 1 and 2. So put that in the curly bracket, second parentheses, and then store into list 1. And so we have list 1 square plus 3, list 1 plus 4. That's the fastest way to do this. Of course, the numbers like this we can all do it by hand as well, but when the number is more complicated, the calculator has advantage. Anyway, so that will be 6. So that is the slope of the secant line. Now the slope of the tangent line. I think we need a calculator after that. So on that side will be the slope of the tangent line. We take the derivative 2x plus 3. Right, the secant line show the mean value theorem, so we have 1 and 2. It might go like this, and then we have the line. So the secant line let the function go like this instead. So there will be a point in between here where the slope is the same as, so there will be a point like this. At this point the slope is the same, the slope of the tangent line here is the same as the secant line. So we make them equal. So we have x to x equal to 3 and x equal to 3/2. It's very important here. The 3/2 has to be between 1 and 2, and indeed it does. It is. If we have more than one point, all of the point has to be between 1 and 2, because the point that has the slope the same as the secant line has to be in between. If it is outside, then it's not really a mean value theorem. It's just a coincidence. Right, so pretty much that. Right. Finding the limits may or may not using the L'Hopital rule. I look at a few of this. So the first one, when x go to -5, so the first thing when we do the limit is just put in the numbers, especially it is not infinity. If it is infinity, that may not be the first thing we do. So we have 0 over 0. This is an indeterminate form. So we can use L'Hopital rule, which means we'll take the derivative of the top, give us 2x, derivative of the bottom, just 1, and then the same way put in the numbers. And since this is a nice number, by nice I mean well defined, we make it equal to the limit. So pretty much just that. Next, 9. we do the same thing. Right. So first thing we put in 0 cosine of 7 times 0 minus 1. Cosine of 0 is 1, 1 minus 1 is 0, so we have 0 over 0, and this is indeterminate. Which means we'll use the Hospital rule. If it is not indeterminate, do not use the Hospital rule. Derivative of cosine 7x, that is the chain rule. Cosine of 7x is negative sine of 7x, and then derivative of the box, we have 7. So pretty much cosine of the box, and the box is 7x. So that's derivative of the chain rule. Negative sine 7x and then 7. X squared will give us 2x. Now we're going to put in 0 again. Negative. By the way, let's just rewrite this. This looks a bit silly. So limit negative 7 sine of 7x over 2x. And put 0 in. Negative 7 sine of 7 times 0 over 2 times 0. And sine 0, we have 0 over 0 indeterminate again. For now space. To get the idea. So the Hospital rule again. As long as it is indeterminate, we can use the Hospital rule. Derivative of this will be another 7, so will be negative 49 cosine of 7x over 2, and then we put in 0. Negative 49 cosine of 7 times 0 over 2, which will be cosine of 0 is 1, so negative 49 over 2. And that is a number that is defined, so we make that equal to negative 49 over 2. And also if we from here we can multiply by 7 then divide by 7, because we have sine of x over x. When x go to 0 is equal to 1. Let me put this here. Limit x go to 0 when x means sine x equal to 1. So with that we can make into a 7x, and we multiply 7 here and 7 on the top, and that gives us 1. Right. The next one, we don't really need to use the L'Hopital rule. We just take the one with the highest power, because as x goes to infinity, the only thing that matters is the one with the highest power. And x goes to 0, x goes to infinity, x cancel out, we have 5 over 7x, 5 over 7 infinity, that gives us 0. Right, so those are the limits. So if it is indeterminate, we use the Harper rule. If it is not, or we don't need to use it. Like this one, we can use the Harper rule, but this is a lot better. Of course, if we have something like this, then of course we're not going to use the Harper rule because that is not indeterminate. Or this, if it is equal to numbers, then it is not the Harper rule. Next we have indefinite integral. So this we have the formula, the whole table here. So first we have the power rule. So I do a few of this, and this will write 4t squared. It is better to write 1 over 7 times t, and then it is easier to take find the integral. So for t, it is going to be t cubed over 3, and t will be t squared over 2. The 1 over 7 will stay, and plus a constant c. So we have 4 over 3 t cubed plus 1 over 14 t squared plus c. So it'll be just that. Right, so just a power rule. On 13, we have to rewrite that as y to the 1/2 over 2 plus 4 over y to the 1/2 dy. And to use the power rule, it's better to write 1/2 y to the 1/2, the 1 here at the bottom, so it will be at negative 1/2. Next we just apply the power rule for this one. So the power rule for this is y to the 1/2 plus 1 will be 3/2 over 3/2, and this will be y over 1/2, 1/2. So 1/2 plus 1 is 3/2. Negative 1/2 plus 1 is 1/2, and any constant in front will stay, and plus c at the end. Now next, divide by 3/2 is multiply reciprocal. So we end up with 1 over 3 y to the 3/2 plus 8 y to the 1/2 plus c. Of course you can rewrite that as a square root, but we don't need to. Right. Next we'll skip 14 and we'll 15 instead. So it is easier to do this if we multiply it out. So sine of theta, cotangent is cosine over sine, and cosecant is 1 over sine. Multiply it out, sine and sine cancel. We have cosine theta, and multiply this, we have just sine and sine cancel, just 1. Now we integrate. Integral of cosine is just sine, and integral of 1 is going to be theta plus c. So integral of a constant is equal to a variable, and I don't know why I have the minus here, why it should be a plus. So it's a plus, and yeah, it should be that. So that is 15. 12, 13, 15. Next we have initial value problem. Both of these are initial value problem. We have derivative equal to something. On number 17, instead of the v is the velocity, which is the derivative. Number 17 is that. So we have s prime equal to cosine of pi over 2t. Right. Now we just this is the derivative. To undo the derivative, we do the integration. So now we have s. To undo this, we're going to do the integral. Right. Actually, the formulas that we have here is not right. So I'm just going to do this, and we're going to study this in section 5.5, so it's not here yet. So the formula will be somewhere in the note. So cosine give us sine plus a constant, except we have to divide by 1 over pi over 2, which turn into the reciprocal 2 over pi sine pi over 2t plus c. Next, we have the initial condition. Meaning when x equal to when t equal to 0, s equal to 1. So we have 2 over pi sine of pi over 2 times 0, t is 0. And this equal to 1. Sine of 0 is 0, so that goes to 0, and we have c equal to 1. And so we have s equal to 2 over pi sine pi over 2t plus 1. Because when c equal to 1, we can put it back in here to get a function. 16 would be similar. We do the integral to undo the derivative, and then at the end we use that condition to find c. Next, we approximate the area under the curve using rectangles. So I'll do one of this. Right. Don't have to be exact. Let's say the function, the curve, go like this, and we'll estimate the area. That goes from 1 to 5. And using 4 rectangles. So from 1 to 5, we divide by 4 rectangles. So let's just find the width. It's 5 minus 1 over 4, which is 1. So 5 minus 1, the total length is 4, 5 minus 1, and then divide by 4 rectangles. So the width for one rectangle is 1. So for the first rectangle, we use the right end point. So use the right point to make a rectangle. And from 2 to 3, we use the right end point. And we have another rectangle. And then 3 to 4 is 4. And then 5. So we have that. We know the width is equal to 1. Now notice that the height of the rectangle, we use this point. So 2, 3, 4, and 5. So we have 4 rectangles, and the area will be length times width. The width is all of them is 1 times the height of the first rectangle is f of 2. The second rectangle is f of 3, f of 4, and f of 5. So we can ignore all the 1. We have f of 2, f of 3, f of 4, and f of 5. Let's use the calculator on this one. Right. I do the same thing with the list open. I don't have to, just do that in the list here. Let's clear the list. So clear L1, highlight L2, clear L. So pretty much we just hit start and edit and enter. So the first and the list 1, we have the values of 2, 3, 4, and 5. And then L2 will be just 3 L1 square minus 2. So we have 10, 25, 46, and 73. We're going to add this in a little bit, but let's just do that on the home screen. So on the home screen, I can do this. Open the curly bracket, 2, 3, 4, 5, and store into L1. And then we have 3 L1 square minus 2, because we have those values. And now to add this, we instead of hit start, we hit second start. Go to math, option number 5. We get summation, and then second answer is 154. So I should write that somewhere. So 2, 3, 4, 5 store into L1, and then L1, 3 L1 square minus 2, and then hit enter, and after that summation of answer, and then hit enter. So the summation, we hit second start, and go to math, option number 5, and to get answer, we hit the second and the negative sign. Of course, second and the negative sign give us answer. So we do that and we add on the list together. So that is 18. Next we use geometry to evaluate the definite integral. So pretty much we just draw the function. Absolute values of x will look like this. And we want the area that goes from x equal to -1 to 5. So pretty much this integral will calculate this area. Right. And to calculate the area, that will be pretty simple because this is the v and absolute value of 5 is going to be equal to 5. And absolute of -1 is equal to 1. So we see that if we want the whole area of the square here will be 1 by 1, and this is half of that. So this area is 1/2 base times height is 1/2. So the area of this square, this rectangle is 1/2. For this triangle, 1/2 base times height or 5 by 5 is the whole square. Have half of that, half of the square, 25/2. So 25/2 plus 1/2 is 13. So we just that. On number 20 it will be a lot easier. Y equal to 6, and we go from -3 to 5. So pretty much the area of that rectangle, length times width, that will be 8. Yeah, but so it will be 8 times 6 will be 48. Right. Next we have the properties of the definite integrals. So when we do this, so first we have the plus in the middle. We can split that in two integrals. The 4 in front of it, that will be a constant. So pretty much this is what we can do. First, we split this in two. And after that, we take the 4 in front of the integral. So we have for integral of function f will be -2 plus g of x is 9. Together is 1. So just 1. And that's it. So we can split the integral and take the constant outside, just like we do with the derivative and everything else. Next, the question asks us to find the integral that is from -1 to 9. Once we have that, we just interchange the limit to get to the second one. Right. So now we start with that. Right. So now the properties is not given here, so we have to know that. So the properties, that is, if we have the integral, so put that instead of go from a to c, we can always go from a to b and from b to c. So a to b and then b to c is the same as a to c, because so now that formula we write like this: the integral that go from -1 to something, and from that something go to 9 will be the same. We can pretty much put anything on the box. Whether t and x is doesn't matter. Now what we see here is this formula they give us from -1 to 2, so that's why we should put 2 in there, and then those numbers must be the same, and it just has so happen that this is going to be this. So this integral gives us 2, and that integral -8, so -6, and so that is -6. Now if we interchange the limit, it's going to be opposite to that, so this is just 6. So a few properties of the integral, we can go from a to b and then b to c. Those numbers must be the same, and we can have anything here as long as they are the same. So -1 still go to 9. The middle numbers are just intermediate. I will have 23 and 24. I'm not sure we can. Our space. Try that. Right. You notice that we skip a few problems in this review because I plan to do that in class. Right. Next, find the area of the shaded region. First, we have this function y equals 4 minus x squared, and it goes from 0 to 3. First, we have to know what is this intersection. So this is where this function equal to 0. So we solve for that quickly. 4 minus x squared equal to 0. So x squared is 4. X equal to plus or minus 2. This point definitely has to be plus 2. Right. So we have two areas. The first area is this one above the x-axis, and this area below the x-axis. So the one above the x-axis, the area is equal to just the integral. And the one below the x-axis, that go from 2 to 3. The first one go from 0 to 2, and then 2 to 3. The function, I put the square in the wrong place. put the 2 inside. Right. Very important that the one that is below the x-axis must have the negative sign. So this has the negative sign. Right. We can use the calculator on this one. We hit math and we go, let's clear this first, math, and go where it said that, and pretty self-explanatory. If you just want the area, of course we can change this to a fraction, 16/3. Of course the area is positive, so that's one correct. Next we do negative, and then the integral. That goes from 2 to 3. Uh, 4 minus x squared and change that to fraction as well, 7/3. As you see, both of these must be positive. Of course, with that negative, it must be positive because area is positive. And we add this to 7 and 16, that's 23/3. Right. Of course, you can use the calculator, but you can also do it by hand. Right, so area above, integral from 0 to 2, below from 2 to 3. Always give the x values for the limits. Right. Next problem, we just use the fundamental theorem of calculus, and this is too fundamental, and we need to know that. So we have any antiderivative. So that is the fundamental theorem of calculus. There will be another fundamental theorem of calculus which has the derivative. Right. So I will not do. Sorry, forgot to update the list. What's that? 6. Now this will be easy. I see 2.5. Right. We write this as 12x is x to the 1/2, and then we integrate, give us x to the 3/2 over 3/2, and that goes from 0 to 9. Multiply reciprocal 2/3. So we have 10/3, x to the 3/2, x goes from 0 to 9, and pretty much we just put 9 in for x. And because that is 0, because 0 raised to any power 0. 9 to the 3/2, that is 27. So 10/3 times 27, that gives us 9 times 10, 90. Right, so that's 27. So we just integrate. We do not have a constant c. Instead of that, we evaluate at the limits, the upper limit minus the lower limit. That will be that. Let's go to 29. Right, first we can of course take the 5 outside, it doesn't matter, but the integral cosecant square this is that, and then we have the formula. There was that. Right, cosecant square is negative cotangent because derivative of cotangent is negative cosecant, so we have 5 cotangent but with a negative x. X go from pi over 4 to 3 pi over 4, right? So we have negative 5 cotangent of 3 pi over 4. That's where we put the top limit, and minus 5 cotangent of pi over 4 where we put the lower limit, and we do that. Cotangent of 3 pi over 4, if we use the calculator, so we do not have cotangent but we have tangent. I forgot the negative sign here. Pretty much the same function but the minus. So let's rewrite that. Cotangent of 3 pi over 4, that's going to be a plus. So we have tangent, so we just have tangent of 3 pi over 4 and then of course we have this for reciprocal, still negative 1 of course, and then cotangent pi over 4 should be 1 as well, so tangent of pi over 4, and then we hit the reciprocal, so that's going to be 0. I forgot that there's the negative 5 in front of it. That is not 0. It's going to be 10. Right, so will be that. So that is the fundamental theorem of calculus. Integrate, we get any antiderivative, and then we evaluate at the endpoints. At the upper limit, subtract at the lower limit. Right. Next we have the second part, or the other part of the fundamental theorem of calculus. So we have something like this. Right. Let me write that out. So we have a function in terms of t. We will evaluate at let's say the function of g of x to f of x, and after that we have the function of x, and then we take derivative. Right, and that theorem says that we're going to put the top function, use that h instead because we already have f, so this is h. So first we're going to put h of x into f of t into the t here, so we have f of h of x, and then we have derivative of h minus, we put in g of x, and then derivative of x. So put in the function and then time derivative, kind of like the chain rule. Put in the function and then multiply by derivative. Now let's look at this one. So first we put in the square root of x into t, so we have 16 square root of x instead of t to the 9, and then derivative of x, this to be determined, and then minus, put 1 into it, and then take derivative of 1. Derivative of 1 is going to be derivative of a constant, which is 0, because the constant derivative is 0. So pretty much just this. Right. Let's rewrite a little bit. Square root of x is x to the 1/2 to the 9 power x to the 1/2. We still have the derivative here. So power to power is multiply those powers, and then we take derivative 1/2 x to the negative 1/2. Now 16 times 1/2 is 8. X to the 9/2 and x to the negative 1/2. When we multiply, we combine the powers. By that we add 9/2 plus negative 1/2, so that is just ax to the 4th power. That is 30. Keep forgotten update in the list 27. 29. Right, I'll do 31 as well. So first we substitute that in here, and then derivative of what we just substitute. For the upper limit, bottom limit has to be minus. We substitute x to the 6 into t, and then derivative of it. Now just like we did before, derivative of a constant is 0, so that is 0. So we end up with x to the 6. Negative cosine square root of x to the 6 is should be absolute value of x. So and then derivative of x to the 6 is 6x cubed, 6x to the 5th, which give us 6x to the 5th cosine of absolute value of x cubed. But because cosine is an even function, so we can drop the absolute values. So that's why they have x cubed or negative x cubed still fine. I mean, cosine of x is the same as cosine of negative x. So absolute values or not, it's still fine. So again, put in the upper limit, multiply by the derivative of the limit, subtract, put in the lower limit times the derivative of the lower limit. One of that might be equal to a constant, which is, one of that might be a constant. Derivative is equal to 0. So that's what we have. That and this, both of them are considered fundamental theorem of calculus. So pretty much pretty much we cover everything that in the list for test 3. Some of the questions we did not do here because I plan to do that in class. Anyway, I hope this helped you to prepare for the next test. Thanks for watching.